Okay, welcome to week number 8, I believe. 1 through 5. Yeah, we've had one exam. We've got 7 chapters here, so we are in week 8 of the semester. Thank you for joining us, those that are online with me now. I'm excited to be here. The sun's out. It's a nice day. And so let's go ahead and get rolling. We're now in our second week after our first exam. Last week we talked about basically a lot of supply chain type problems is kind of where we first started in that. And basically the common thread was there that all of the problems we talked about last week in some way, shape, or form could be drawn out or represented visually using a network or a graph, kind of leaning toward graph theory of the area of mathematics there. And so hopefully you've enjoyed that little change, a bit of pace there. We also introduced a little bit more complex in the one way, just a different syntax in Pyoma with the constraint list and not embracing that set idea. So hopefully you've been able to spend a little bit of time in that because that is a very, very powerful mechanism that you have at your disposal with that tool. Allows you can be able to tackle much bigger problems than you typically would with just MS Excel. And so also during the past week, I was able to go through the partial credit evaluation for exam 1. So you may have seen your score go up a little bit there, hopefully. I basically went through partial credit on the last 2 problems, the 2 big application problems at the end. And so if you have any questions or concerns about that, please let me know. I think I've already had a couple students reach out about the exam question, just trying to make sure they fully understood what they did wrong and trying to correct that as they move forward there. So I definitely encourage that train of thought. And so, as we move from kind of the recent history now toward this evening, we are in a very exciting chapter for tonight. Something I would like to dive more and more into as I continue to teach this class. And this is the idea of MIP problems for the most part. And what I mean by that is that up until this point in the semester, we've been constraining ourselves to have decision variables that are always elements of the real number system, right? They can be floating point numbers, essentially, all the decimals inside there that are included. And so that's great. You can see we've obviously been able to tackle quite a few problems with just that as our tool set. But now we get to make that tool set a little bigger, and we get to explore the idea of, well, what are the implications that happen when we say, okay, not only can I have decision variables that are real numbers, but also have decision variables that are strictly constrained to be integers. Or even going a step farther, what if I made them binary in nature, so just zeros or ones there? And so we'll take a look at a little bit of that. I'll talk maybe briefly toward the complexity of that, but we won't dig too much into the computational side of things. But really, what I want you to take away from tonight is, yes, there is a computational expense, but even more so that there is a whole nother realm of problems that we can now work with, a whole nother of logic conditions, kind of if then this type stuff that we can now model in our optimization models, which then again opens the doors to much more interesting problems. And so, with that being kind of the trailer, the teaser, if you will, for the evening, let's go ahead and hop into the lecture. So I'll transition from my Canvas tab to my tab here running Jupyter Lab inside of the Docker container for this course for the semester. We go to lecture. We're still in linear programming. It's great to see now that we're almost exhausted all of these child folders here. We are on integer-mip here. And I'm just going to go ahead and toss out these two at this point, and I'll run this one. All right, so chapter 7 is where we sit in the textbook. Integer linear programming is the title itself. And again, as I've already discussed, basically integer linear programming adds us a new layer of flexibility, a new set of problems that we can embrace and model. But it's not just free, so to speak. There is a computational cost associated with it. And that computational cost largely is going to be hidden away from us as students of this class or as the modeling that we do. What do I mean by that? Is there'll be a few tweaks you have to do in Excel. There'll be some different variable types that you have to describe in Pyomo, but that's kind of it in a lot of ways as far as the actual syntax of it goes. Yes, there's going to be some different techniques from the modeling side of things. When we write a constraint, we may be thinking about something slightly different there. So that may show up. But other than that, a lot of the complexities are going to be hidden away from us at the solver level. And so typically I want you to be able to acknowledge the fact that, yes, this is a different solver. For instance, up to this point in time with real decision variables, it's going to be in some form of the simplex algorithm that's going to be at play. And so tonight there's actually going to be a little bit different techniques and things like branch and bounds, and there's cutting plane algorithms as well that also are kind of layered on top of that kind of base algorithm. And so, as I talk about the computational complexity of this, you may be asking yourself, okay, is there times where I can get by with just real decision variables? And even though the physical quantities are actually integers in nature, could I solve it with reals and then get fairly close? And the answer is yes. This is actually a technique you could use, and we've kind of been using it throughout this point in the semester, is just say, okay, as long as the decision variables are going to be fairly large quantities and things like the unit profit contribution, if I'm maximizing profit for each one of the units of my decision variables is fairly small, then yeah, I can get away with the idea of saying, okay, yes, that's really supposed to be an integer, but I'll treat it as a real number. I'll truncate maybe the results of the decision variables at the optimal solution. So I make sure that all my like less than or equal to bounds or constraints are satisfied. And then I'll end up with a fairly good solution. And so fairly good solution may be good enough for me as far as if the computational costs are too much. And so that is one way to approach it, but just need to acknowledge in that fact that yes, I may not be truly optimal, but I could get a fairly good solution if I go through that technique. The other things to note, which is I kind of talked to a little bit last week, is that there are times that you'll be running a linear programming model and you will not have told the solver to ensure that the decision variables are integers, but they may still come out as integers in the optimal solution. Classic examples of that, as we saw last week, remember the very first part, the assignment problem, the transportation and transshipment problems, we always were saying last week that the decision variables had to be real numbers in the optimal solution. But if you go back and look at the notes, they also ended up being solved to be integer values. And that just had to do with a special structure that those problems actually held themselves there. And so that is also a possibility. And typically you will see as we talk through some of the computational details and kind of see the outputs of PyHomo a little bit, that even if you did declare those as integers, what it's going to do is it's going to first try to attempt to solve an LP relaxation of the problem. We'll again hold that term shortly because we'll define it. And then basically what that means is it's going to solve it with real decision variables first. And if it happens to be solvable where those optimal or decision variables are integers at that point, it would just break out at that point. So not terribly something you need to worry too much about given the nature of how these solvers will operate. So as we kind of get through the forward part of the lecture here, we kind of get into some vocabulary type words here. 7.1 just kind of lays out this idea of there are multiple types of linear programming problems that fall into this idea of having some integer type decision variables. The first one, all integer linear program, just like it sounds, the all integer part is referring to the decision variables, and it's just basically stating that every decision variable is going to be constrained to be an integer. Probably maybe more popular when you look at the grand scheme of things is that second one in the unordered list, the mixed integer linear program. I'm also seen that a lot of times where they will just drop the L out of that and they'll call it a MIP, as in mixed integer program for short. And that basically stands for the idea that you've got a mixed bag amongst your decision variables. Some of your decision variables may be integers, some of them may be reals, and I would even include in that some of them may also be binary in nature. That would all fall into that second one. And then the bottom one there, 0 to 1, linear integer programs is the definition they give in the book. Basically, think of all these as having decision variables where every one of them is binary in nature. And when I say binary in nature, think of a light switch that's on or off, right? There's only two states to it. And typically what we'll do is represent that as being a 1 or a 0. 1 if it is active and 0 if it is not. And so you can see examples of that as I just wrote out some very simple linear programming models in the figure below. I don't think I've defined it yet, so it'd be a good point to say this symbol right here. I'm kind of circling with my cursor. That is the symbol for the set of integers. You kind of saw me earlier in the semester write a scripted R for the set of real numbers. That scripted Z is for the set of integers. And so in this far left case, I'm saying both the decision variables are elements of the integers. Here I'm just saying just the x1, so we'd assume that the y is also a element of the real. And then this far right one talking about the LP relaxation is a case where they're both elements of the real number system. And so bringing us to the point of what is the LP relaxation? Well, the LP relaxation of a mixed integer linear programming or an all integer linear programming problem would be when you basically look at that problem and then drop all the integer constraints. Basically, let those values go back to real floating point numbers, and then that is your LP relaxation of that original problem. As always, if you have any questions with what I'm going over at this point, definitely feel free to unmute yourself and put something in the chat. So now that we've gone through kind of the vocabulary part of the evening, let's go ahead and talk about a fairly simple problem here. This is a problem that I would expect you to solve very easily without the elements of the integer statement down here at the bottom. We just have two decision variables, maximum 5x plus 4y, subject to a couple constraints and the non-negativity constraint, as well as the requirement now that x and y are elements of the set of integers. Well, before we go ahead and solve that, let's go ahead and first look at the LP relaxation. So again, the LP relaxation basically would ignore this bottom line where it says that the two decision variables are elements of the integers. So let's go ahead and hop into this. It is a two decision variable problem, so I could do it graphically, and we will at this point, just so I can highlight some of the visual representations of the all integer solution. But first, if we're solving the LP relaxation, this goes back to the chapter 2, right? When I first showed you guys how to solve graphically these types of problems. So if you remember, we basically were going to start basically drawing regions of the Cartesian plane that satisfied individual constraints. In this case, most of their constraints are less than or equal to, so we end up with these shaded region. In this case, we're looking to identify the feasible region, so that's the intersection of these two shaded regions here. So we end up with a shape that looks like this. It's a fairly simple polygon with some vertices 0, 5, 3.75, 1.25, 4.5, and then the origin. Next, if you remember, I'd look at the objective function, and then we would set it to a certain value, plot the line, and then try to increment that value over and over again to see where it started to escape the feasible region. In this case, the optimal solution ends up like this, where the objective value you can see is 23.75 units, and the optimal solution occurs at 3.7, 1.25. So prior to tonight, you would say you're done with this problem. I found the optimal solution with the decision variables being members of the real number system. That sounds great. The big change here tonight, though, is that we're not finished. All we've done at this point is solve the LP relaxation problem. And so what do we do next? Well, back earlier in the discussion, I said, well, one technique would be to say, okay, I found the solution to LP relaxation. If I look at my constraints up here, they're both less than or equal to here. X and y have to be greater or equal to 0. So what I'm thinking is I could basically apply a mathematical floor method on my two floating point values that came out of the optimal solution and come up with a relatively good solution. And so when I say mathematical floor, I'm talking about, I'm looking at those two floating point numbers there. I'll just lower this one down to the nearest integer, so 3. And I can lower that one down to the nearest integer, basically removing the 0.25 and placing with zeros, and it'd be 1. So I can say, okay, the solution, I won't say the optimal solution, but a solution would be 3, 1, which would yield an objective value of 19. Okay, that's better than nothing, probably. And so how does that then compare with what would be the optimal solution if I did actually acknowledge that those values had to be integer? And so you may start asking, okay, how would I go about solving that? Well, one way graphically to think about that would be if I took a look at this shaded region and I plotted all the different points being the ordered pairs where both the x and y axis were integers, and it also fell inside of the shaded region or at the boundary of the shaded region. And so that's what I've done with just this little bit of code here. And I now have those red dots there. All those red dots, as you can see, are either on the border of the feasible region or contained inside of them. So they are all feasible solutions. And one thing that would be attached to us now, if I kind of go back to my graphical approach of solving it, would be to do that same business or same method with the objective function where I pick a value for it and I start to increment it. But the condition now is that we need to get the highest value of the objective function such that that line must go through one of these points. And so we could play with that for a little bit, and we would eventually find out this would be the optimal solution. Notice here, I've got the green line. It's set at an objective value of 23, and it goes through this solution right here, 3, 2. Notice they're both integers in this case. It's also on, I think, the border of that feasible region or inside of it. Let's zoom in a little bit. Yeah, it appears to be right on it. And so this is where we would say is the optimal solution with the acknowledgement that the x and y has to be elements of the integers. And that's kind of the idea of the graphical solution in this case. But what if we compared this back to our earlier statement of just rounding things down, right? Well, notice here my objective value is 23. When I just said, hey, I'm going to round it down, my objective value is 19. So it is a substantially better solution than this kind of this heuristic, if you will, of just truncating these values from the LP relaxation. And I guess you may ask, well, how good is this compared to the LP relaxation? Well, we're at 23 now when I force it to integers and pursue the true optimal solution at the integers. And before, it was just 23.75. So we're really quite close to the LP relaxation problem there. It's optimal solutions, the objective function according to the LP relaxation there. And so I guess before I proceed any farther, I guess any questions, concerns up to this point? Well, I'll pause a little bit. I know I've had a few people hop on a little bit after I got started. Okay, not hearing anything big there, so let's go ahead and continue. So one of the last things I was doing there is I was comparing the LP relaxation's result of the objective function to the solution that I got from the integer problem, where I actually embraced the idea that x and y had to be integers. And that's kind of going to be a familiar idea moving forward, just because of this LP relaxation is going to be able to establish these bounds. And so I've got a couple statements here to kind of reinforce this. Basically, it's the idea that for a maximization problem, that LP relaxation is going to be an upper bound for any possible solution that we get when we enforce the decision variables to be integers. Likewise, if it's a minimization problem, the LP relaxation is going to act as a floor, kind of a minimum bounding value that is going to be in place when I go to pursue a solution where the decision variables are indeed integers there. And that's a very important concept because that type of idea of being able to judge the quality of a solution is kind of baked into some of these different algorithms that we're going to be under the hood using this evening. And so what do I mean by baked in there? Well, it allows us at any given step of our solution process to be able to judge the quality of such a solution. And that leads us to the ideas associated with the MIP gap. And so I may have mentioned this a little bit earlier in the semester, but when you're solving with integer decision variables, a lot of these solvers will have what's called an integer optimality condition. In Excel, the solver, you go to solver options. It's right here on the all methods, solve with integer constraints, integer optimality, and I think 1% may be the default value there. What does that mean? Basically, that means that as the Excel solver is trying to solve the problem, assuming we have some decision variables, or at least one decision variable that has an integer constraint on it, is that it's going to allow it to stop early, terminate execution, if it can detect that the current solution it's sitting on is within 1% of the optimal solution. Um, you have a similar idea also inside of the Pioneer solver that I'll show you in a second. And so that's somewhat of a big deal. Not so much for the problems that we typically are working with this semester, largely just because we're in an academic situations. It's kind of a playground. It's fairly safe. We're doing fairly small and controlled models. But if you get into the real world, so to speak, outside of the friendly confines of academia, and you're working on bigger problems, then the solve step, instead of taking tenths of a second, which is probably what a lot of our solvers take right now, it could take a long time, considerable amount of minutes, essentially. And so in those situations, depending on the scenario or the application you're applying to, that may be a deal breaker. And so one thing you could do in there is to let it stop early with the knowledge that I may not be at the truly optimal solution, but I mean, if I can get done early and be at a 99% of the optimal solution, most of the time I'll be okay with that, right? And so that's the whole idea behind this MIP gap. They call it integer optimality inside of Excel. If I scroll down a little bit, I also give you some information with Pyomo. But before I do that, it looks like I've got here, when you see it out of Excel, there is a little bit of a difference. What I'm showing here is one of those reports where we can show specifically the answer report, just like you can show the sensitivity report. And at the top of this worksheet, you'll see two very small differences in row 4 of the worksheet itself here. Let's start with the one on the right. Solver found a solution. That's great. All constraints and the optimality conditions are satisfied. This means it did not terminate early. If I go to the left-hand side, solver found an integer solution within tolerance, and all constraints are satisfied. So this is where it stopped early in Excel. So that's one of the things you'll have to take note of as far as if that really matters to you and you're working with a model that has an integer decision variable. You'll go through and you'll solve the model. And I think the only place it shows you this is in the answer report. So you'll have to get in the habit of exposing that answer report and going to take a look and say, okay, did it stop short or did it achieve the true optimal solution? In Pyomo, the way you control this is by passing a parameter down to the GLPK solver, which is what I'll show, just a little snippet there. And so here I've got MIPGAP as the option name. And so this is option name is specific to like GLPK solver. You'd have to look at the documentation for it and then be able to just determine, okay, it's got a MIPGAP option that you can pass down into it. It's expecting a floating point number. So like just like above, the Excel solution wanted a 1% integer optimality tolerance or MIP gap. Here, I'm also doing the same thing. I'm putting in 1%. So all I'm doing is saying solver. After I've created a solver, just like we have all semester, look at the options. This options in the Pyomo solver is a dictionary. So think key value pairs. And so the key here is called MIPGAP. Again, that's specific to GLPK. And then we're saying that's equal to this MIPGAP variable, which is just this 0.01 value. And then you would go ahead and solve it as usual. In Excel, it shows you right here whether you stop short or not. This is the example problem. If you remember from our first lecture, chapter 1, where you're dealing with some cabinets and I asked you to try to take a stab at solving it. Here's actually the solution for it. Again, enforcing the integer values for the number of cabinets completed. And it would typically show somewhere down here. And so this is a good place where I can see the output of the GLPK solver. Notice up here, it's doing some pre-processing right there. And kind of the first interesting thing I'd like to note is what's one of the first things it does? it solved that LP relaxation. So what did it do? It basically dropped this constraint and solved the model assuming real decision variables. And it says right here, I was able to find an optimal LP solution found relative to that LP relaxation. Now it's got that LP relaxation solution in hand, and it starts with the integer optimization. And so this right here is kind of where it usually talks about the steps that it's at. This is a fairly simple model. We maybe able to see one model, maybe our second example. If we do it in Pyoma, would show a little bit more here. But no, there's basically 1, 2, 3 kind of steps in here. And this is where you would see it working. And so on a harder model that would take several minutes to solve, basically there would be multiple rows, more and more rows of this. And basically you can, if you t it equals true and print it off the command line, you would basically see it working and print something to the terminal for every step that it achieves. And what you would be looking for is this value here on the right-hand side basically tracks how close it is to what it knows is optimality there. And you would be watching that number creep smaller and smaller down. It may start off at like, oh, it's 44%, then it'd be 32%, then it'd be 10%, then it'd be 5%. And then maybe you have a MIP gap that's at 2%. And so you may see it 5%, and then it drops down to 1.8%, and then it would say it terminated there. In this case, it's a very simple problem, and I don't believe I specified a MIP gap. Oh, I did specify a MIP gap here of 1% tolerance, but it did not stop short here. It actually tells me the true integer optimal solution found. It didn't say some statement there with the MIP gap. And so then after that, you basically treat the model as usual. You can say model.display, and basically what Pyoma does is it takes the results from the solver and stuffs it back in the model. So if you remember way back in chapter 1, this was the number of contemporary cabinets, and this is the number of farmhouse cabinets, and the resulting profit contribution there. All right. So I think that gets through most of the kind of high level discussion to start off the lecture. Basically just the idea of being able to discuss these different types of models, kind of vocabulary stuff. What is a MIP model, for instance, here, a mixed integer linear program there? What is LP relaxation? How does the kind of algorithm work a little bit? Hopefully you're starting to see some of those things there. And so with that, I think we got 3 examples to go through tonight. Are the applications of these binary decision variables. So again, binary decision variables are great because they are able to do yes or no type of decisions. And the example we're here talking about today is capital budgeting. So here we're going to have a series of projects, and the decision is going to be, should I undertake or proceed with this project or not, essentially. And so that is a very much a binary thing. Either we're doing the project or we're not doing the project. And so let's go ahead and look at some more details of this problem. I'm going to try something here, just if you don't mind here. This is called Excalidraw. This is something I've played with a little bit in the past week or so. We'll see if this works with the tablet very much, or the tablet I've got here, but we may see it work reasonably well. What this is a online drawing tool that I've started using for like workflow type stuff. Like you can draw things like here. Say this is a text. You can group things together, so that's one thing. You can size it, all these good things, just kind of to flow things together here. So let's give this a shot tonight. All right, so bookstore growth problem. So the bookstore growth problem is about a bookstore. Think of this as maybe the campus bookstore, and they're wanting to undertake a few different projects here. The projects that they're considering is the website, the warehouse, the clothing, computer, and the ATM. Each of them they estimate to have a certain net present value of a return, which is here. Everything's in thousands of dollars. But they don't know if they're able to afford all of them, or they're certain they can't afford all of these. and they don't know what subset of them they should pursue so that they don't break the budget, as well as they want to maximize this net present value for return. So if we look at the funds, well, we've got this many funds, depending on the 3 years we're working on. And then as far as the projects, they have various costs over this 3-year period as well. The other thing besides the budget factor that we need to worry about is the statement right up here, basically stating that there's not enough physical space to do both the clothing and the department and the computer departments there. So we have to be able to enforce that as well. All right, so let's give this a shot. I'm interested to see how it turns out. Ooh. Yes, I'm quickly going to bail. Thank you for that experimentation there. Let's go back to the normal one here. All right, so the bookstore. Well, one of the things that we need to do is talk about decision variables. And our decision variables really are going to come down to the decision for every project, right? You can either say, hey, I did this project or not. And so let's talk about those. We need to define some variables for it. Well, let's say x sub web. Let's say it's, oops, not an element of the integers. That's a little too much. It's binary, so it's an element of either 0 or 1. And this is the decision to do the website project. So we'll say website project. And very similarly, we'd have another one for each one. So I'll say x of where, x of clothes, pump, and x of ATM. And this, of course, is the warehouse, clothing, computer, and ATM. Okay, now that we've got decision variables, we typically move on to the objective function. Again, the objective of this problem is to maximize the net present value. So hopefully you're already saying, okay, that's fairly easily. One thing I could do is say maximize these decision variables with kind of the sum product, if you will, linear combination of these values here. That sounds great. And also, one of the nice thing about this is with these binary decision variables, that makes perfect sense, right? Because if I decide to do the project, it'll be 1 times the value. But if I don't decide to do the project, it'll be 0 times the value. And that 0 times the value will basically make it so that the net present value is never used or realized, if you will. So we'll say I'm going to maximize the linear combination of these decision variables with respective coefficients here. So it'd be like 120 x sub web plus 85 x sub where plus 105 x sub comp plus 140. Oh, slight error here. 105 is for x sub cloth, then 140 for x sub comp, and then 70 for the x of ATM. There we go. So that allows us to maximize the basically total net present value of these projects. And then subject to a series of constraints here, let's look at the budgetary types of constraints first. So we basically can't run out of money in any given year. So one thing we could do is look at the cost of a given year and make sure that the cost does not exceed the available funds. Well, again, we can just basically take this times the corresponding decision variable, and using those ones and zeros in there basically allows us to know that cost was added or not. And then we can say that's going to be less than or equal to the available funds in the given year. So we can say something like 55 x of web. $45 x of wear, $60 of cloth, $50 of comp, and $30 of ATM. And here we would say that's got to be less than or equal to 150. So that line here basically allows us to say that we're not going to run out of money in year one. And then we would do the same thing 2 more times. So the second one is really just a carbon copy, except I'm moving one column over here. So I will quickly write that. That's year two. And year three is more of the same, but it'll save us a little bit of writing here, right? Because the website needs to be considered for year three. The warehouse needs to be considered for year three. But then I skip to the computer department. And I also leave out the ATM. So it looks something like that, right? Fewer terms than the last one. So now that we've written constraints for every one of the years and funding, there is still one more thing that we need to look at. That's this last sentence right in here. The bookstore does not have enough space to create both the clothing and computer departments. So again, this idea of binary decision variables allows us to capture that logic. Because I could say something like, well, computer as well as clothing. The computer department is X comp. The clothing department is X cloth. And I could say if I cannot do both of them, I would say that must be less than or equal to 1. And hopefully that makes some good intuitive sense for you. These are both binary decision variables. So if I don't do either of them, I have 0 is less than or equal to 1. If I do one of them, then I have 1 is less than or equal to 1, which is still true. But if I do both of them, it would be 1 plus 1, 2, which is not less than or equal to 1. And that would be my condition to say that that is not a valid solution. Space consideration. Typically at the bottom of these things, I would say X and Y are greater than or equal to 0. But here I've already made the statements up here that X and Y are binary in nature, so there's only one thing we really need to say it there for that non-negativity that I usually write. So I guess I'll pause a few seconds here just to see if there's any questions. Okay, sounds like everybody's doing okay. So let's go ahead and do this one in Excel. It's fairly small, and so we can just make sure everybody's clear on how to say binary, I guess, in Excel versus an integer. So first I'll see if I can copy some of this over. Wouldn't be too bad. Zeros in here instead of the dashes. And then we have the year. So let's consider that all the data side of things. And we'll build the model out to the left here. So the model, first thing we need to think about is decision variables as usual. I'm somewhat thinking orientation and the ability to use the sum product here. So I'm going to just take that as the column it is. And there will be the decision variable cells. We have an objective function. So to maximize the total net present value. So again, we should be able to sum product in order to create that first objective function. And then we've got constraints. I think there was a total of 4, 3 years, and then plus the space one down here. So these are all less than or equal to, so that's kind of nice. Won't always happen that way. For the year funding, I can just reference over here and drag across. We said that was 1 to make sure that we couldn't do both the computer and the clothing department, I believe. So maybe we start with that one. So computer plus clothing department. And then these will be some products for the fundings of the projects and the different year cost there. Unfortunately, I can't really drag this one, so I'll just type it out 3 times. It's not too bad. Just like so. All right, so now that I've got the model built out, we go to the solver dialog. So data and solver. My objective function is right here, same as always. I want to maximize the net present value. I want to change these cells here. That's good. I can add all the constraints all at once. Change that to simplex LP there. So if I was to hit solve right now, this would solve the LP relaxation of the problem. So let's go ahead and do that and just see what happens. Okay, I end up with a solution. You can see the solution is clearly not going to work for us, considering the fact that we need to have kind of binary decision variables that state the end result here. And so these are clearly not ones and zeros, right? I've got a bunch of floating stuff in here. And so we need to do a little bit of work here. So let me go ahead and snip this. It may be interesting for comparison. This was the LP relaxation. So how do I change it now so that it's actually solving it with these being considered binary decision variables? Well, that's done up in the solver dialog box. It's really treated more as a constraint than anything. I can come in here and say add. And I think I mentioned this earlier on the semester. We've only been using the top three here, but notice there's int and bin. Int obviously standing for integer. Bin is what stands for binary. And so in this case, we want them to be binary in nature here. And then I can just select my decision variables. And now I notice the statement here that all my decision variables are now binary. So I'll go ahead and solve it. And then here's where it's reporting that same statement, all constraints and the optimal conditions are satisfied. So I'm going to say OK. And we end up at the integer-based optimal solution here. So what does that mean as far as interpretation? Well, it appears we're going to pursue the website, the computer department, and the ATM department. These three right here are the projects that you would move forward with. As far as the estimated net present value is 330,000. Notice I talked before, this is a maximization problem, and that the LP relaxation was going to be an upper bound to that. And so here I've in my snipping tool brought out the solution for the LP relaxation. Notice it had a slightly higher value, 350.7, versus the 330 there. So that shouldn't be a surprise to us. This is slightly lower. And then on to the other things that may be of interest here is the associated with Slack. How much do we have left over in the budget for every year? And so you could clearly show that by just taking the difference there. So $15,000 is remaining in the first year, and then $5,000 in the second and third year there. So really the only big difference that I've shown you this evening is this right here, where I'm talking about the idea that I've got a binary-based decision variable instead of a integer-based or a real number like we have been seeing. The real numbers, basically you don't have to put that in there. It's just going to be assumed that the decision variables are real numbers unless you change otherwise. And again, also, we talked about the MIP gap earlier. Notice I go to options here, and this right here is where that MIP gap's in place. And you can make this a floating point number. Like I can set that to 001 if I wanted to there. But as you saw, the default was just 1%. So I guess any questions, concerns on doing this in Excel or just the problem as a whole? I got a question of what version of Excel is that? Ooh, let's see if I can answer that. Usually there's like a help about or a tools about. Honestly, I'm not sure how to show that. That's a new question that I haven't really been asked. Oh, here we go. Product information. It's the Excel that comes with Microsoft Office Professional Plus 2016. Or I guess down here is even more specific about Excel. It appears to be Microsoft Excel 2016 version 2502 build 16, blah, blah, blah. So that's the technical answer to that, I guess. Okay. So if there's no other questions I can entertain, then let's go ahead and move on. This out. I'm usually I save this off, so give me one moment. Okay. Let's go through here just to make sure I didn't get off too much or fall along. Here's also the PyOmo solution, that same problem. The biggest thing here I'm doing is saying domain. Usually we would have said pe.non-negative reals. And now notice we're saying pe.binary. So that's how you indicate to PyOmo that I want a binary decision variable. Other than that, all this other stuff should remain similar to what you've been doing in the past. I'm not doing any MIPGAP things, nothing to pass into the solver here, just passing it the model, teeing it out. Just like before, it solves the LP relaxation, found it, and then started on the path toward an integer optimal solution, which it also found here. And it printed back the same solution. So that's all good. All right, so as a second example here, let's kind of talk about what we discussed a week ago. A week ago, we talked about distribution systems. We have these network-based models. And so tonight, we'll look at that with a twist. And the twist is going to be the fact that some of the nodes in our network model are going to be, we'll say, optional. And so what I mean by that is that last time we had the origin nodes and we were sure that those all existed. Now they're kind of conditional on the fact that, okay, we could purchase that farm, we could acquire this facility, if you will, and then it would be able to generate some output. But if I don't acquire the facility, it's not going to generate any output, of course. There, so now it becomes conditional whether I get to source stuff from that location or not. And so to make that a little bit more tangible, let's look at this farm purchase as an example. Basically, you've got these farms that you're looking to purchase some of. And so you've got 6 different farms to possibly purchase. We've got fixed annual cost here, plus projected annual harvest here. Okay, so it costs per year to operate the given farm, the amount of output of the given farm that we're going to have here. Okay, the company also has 3 plants, A, B, and C. Basically, the farms are feeding the plants, if you will. They have a certain capacity, 12, 10, and 14. Again, in thousands of pounds or thousands of tons here. And we have shipping costs because there's different distances between each farm to different plants here. So we've got a typical array of shipping costs to move from farm numerically 1, 2, 3, 4, 5, 6 to plant A, B, and C here. And so the question is, which of these farms should be purchased? Okay, that's one question. And then the other question is going to be, say I figure out which farms to purchase, then how do I determine the strategy to move the crops from the farms to the plants? And so that's what we'll dive into this evening. All right, so let's talk about farm purchases. So this is a little bit more complex of a problem. It may help to have a image. I'm always a big fan of images here, so I went ahead and downloaded the lecture notes, and I think this one has a decent image that I have tied with it. There is a transportation element of this, so let's look at something like this. And so think of kind of this in your mind, that here is the network diagram for this problem. I've got farms on the left. They're moving crops to plants on the right. On the left is the, I believe, capacity of the farm, its annual harvest, and then the right is the demand, all in the same units of thousands of tons. And so we have these options in order to move goods from a given farm to a given plant. The only big thing here is left-hand side. Last week I would have just given you the, hey, there's 6 farms and we're done with it. But now it's 6 farms, but we're not necessarily going to have all 6 of these at the end, right? Because the idea is we're purchasing these farms and we're trying to minimize this overall cost. And so kind of keep that in your mind as we work through this problem. And so as I talk about that, hopefully you're starting to think about, okay, I need to determine things like the sets, the parameters, the objective function, decision variables, all that. And so let's start with just the sets. So what are the things we're actually talking about? And so we'll say sets. Well, one of the things there are, they're farms. Let's say that's the set F. The farms are numerically labeled. So 1, 2, 3, 4, 5, and 6. And there are plants. Plants here being factories, not plants like grow in the ground plants. A, B, and C. Okay, so now we've got farms, we've got plants, that's great. I think that's really all that we're dealing with. We have some parameters, though, some data points that we have to work with. I'm thinking first here on the left-hand side, I've got numbers, each of those nodes that represent the farms, that's the harvest. Let's let H of F be an element of the reals. For every F, it's an element of F. And let's think of this as the harvest of a given farm. What else do we have? We've got the demand of a plant. And so let's call that D. We have one of these for every plant. All right. What else do we have? We had things like the fixed cost of each farm, if you remember right. So we'll just call that C sub F. Or annual cost. And then we also had some shipping costs. There's a little matrix there of shipping costs from a given farm to a given plant there. So as I'm saying that, hopefully you're hearing the things that I'm saying, shipping cost from a farm to a plant. So you're thinking multiple indices on that. We'll just call that S for a shipping cost. And this is a shipping cost. I should really say this is a unit shipping cost. from farm F to plant P. I believe that's everything for us. Let's now get down to decision variables. And in one sense, you can think of decision variables as just like we did last week. We have to decide how much of the crop to transition from a given farm to a given plant. And so let's just go ahead and write that one. We know that's going to be part of the problem. And so it says something like let x of f comma p. Here, that could be an element of the reals. That makes sense as far as maybe these are in tons of crops. So we could say there's 0.357 tons of a crop. So that makes sense. And so that's some of the reals. And I've got to say that's for every f in f and for every p in the set of p. So this is again the quantity to ship from farm F to plant P. All right, so that's good. Now here comes the kicker for the evening, is that that's not the only type of decision variable we have, right? We also have to capture this decision of whether to actually purchase the farm or not. And so we need a totally different decision variable for that. It's not going to have two subscripts, right? It'll just have one. It's whether I purchase the farm or not. So let's just use y sub f. What is this an element of? Well, it's the purchase to buy the farm or not, right? It's got to be binary in nature. So we'll write it like that. And I need one of these for every farm in the set of farms. And I'll say this is decision to buy farm. F. All right. Now we're down to the model. Well, the model is really describing us a situation where we're trying to minimize the overall cost. I'll say minimize. And the overall cost, when I say that, I need to be thinking of two different elements of the cost. There are elements of the cost that are tied into these fixed annual costs. And there's also elements of the cost tied into this table down here, talking about moving goods from one place to the other. So maybe we tackle this one first, this fixed annual cost. To minimize that, or to write it first, to write an expression for that, we would basically take the C sub f parameters up here, and we need to take each one of those, multiply it by the decision to buy that farm or not, and sum them all up. Very similar to what we did before with that bookstore growth problem, except for instead of looking at maximizing a net present value, here we're just trying to minimize the cost. And so I'm going to write that with a summation. I'll say I want to sum across the set of all the farms, and I want to take the product of C sub f times y sub f. And so that small little expression there is what's allowing me to say I want to look at the summation of all the fixed annual cost. This is the annual costs. And do notice here, since that y sub f is a binary decision variable, that if I choose to purchase the farm, that'll be a 1, so that cost will be included. But if I do not choose to purchase that farm, it'll be a 0, and the cost will not be included in that sum. And then I'll say plus. And then over here, I need to write an expression for the shipping cost. Well, we did that all last week. Hopefully that you can remember we were writing things like a double summation in this case, where I would say, loop through all of the farms that are the set of farms, and also loop through all of the plants of the set of plants. And I want to take S, I'll use first, F comma P, that parameter that talked about the unit cost when I'm moving from a given farm to a given plant. And I want to multiply that by how much I'm moving between that farm and that plant. So that's where I end up with an expression like that. And so this is the shipping cost. And we're running out of some real estate. So let's make the paper bigger. And so again, those summations, the two things, the annual cost plus the shipping cost is the total overall cost of this problem. And we want to minimize that. So now we put our ST, our subject to, and we start our minds toward the constraints. So the constraints here, we think about it, we got a couple different types of constraints. One is for the plant demands. We want to be sure to satisfy those. And the other is for the farm supply side of things. Let's start with the plant demands. And so we would need to write a constraint now to basically say that every plant has its demands satisfied. And so I think last week you saw me do this quite a bit, as I would kind of start from the right-hand side and work my way back to the left. And so let's do that again. And so I would say something like, for every P that's an element of P, what am I trying to get to? Well, I'm trying to satisfy this demand. So we call that D sub P above. Here, I'm going to say that I want to be equal to the demand. And then now I start looking at that diagram. That diagram that I have in my mind is, I think, right here. If I'm looking at a plant, I'm looking at all of the arrows, one from every farm that's going into that plant, and saying, okay, I want to sum up all that flow that's coming into it. Well, to say that mathematically on the left-hand side, I would say something like, well, I've got a plant. Now I want to sum across all of the farms, and I want to somewhat, well, I want to sum all of the quantities that are moving from the farms to that individual plant. And so that's what I have there. Okay, now that should look very familiar from last week. And so now let's work on the supply side of things. Make sure we don't kind of overextend what we promised from every farm, given the projection in the harvest. And so in this case, I'm going to have to write a constraint now for every farm. So we kind of reverse it here. And I want to make sure everything that leaves the farm does not exceed some upper threshold. I think we called above the harvest of the farm H sub F. And we would want to write a summation on the left-hand side that went across all the plants and tried to sum up here everything that was leaving that farm, which is what I've got at this point. So this is good up to this point, but there's a small bit of extra thing that we need at this point. This would have been good for last week, assuming that all those farms we knew were going to be there. Well, now we're in a situation where we're going to essentially purchase those farms. And, well, if I don't purchase it, that means this harvest value needs to go to 0. But if I do purchase it, I need the harvest value to be whatever H sub F is. So the easiest way to do that is to now take that binary decision variable and take it right here. So that it's the product of that binary decision variable times the harvest. And if you take a moment to think about that, that works out nicely, right? If we buy the farm, that binary decision variable goes to 1, and we end up with the right-hand side being the quantity of the harvest for that farm. If we do not buy that decision variable, or do not buy that farm, that decision variable goes to 0. Now it's at 0 times the harvest, that right-hand side renders to 0, and it's basically as if that that farm does not have anything to offer, no harvest. And so that's one of the beautiful things about these binary decision variables. Maybe it's important to highlight that right there is a big thing. All right, so at this point, we're down to kind of non-negativity areas here. And so we don't necessarily need to write anything for the binary because we said it's binary, but it would be a good taste to say except f comma p must be greater than or equal to 0 for every f that's an element of f, for every p that's an element of p. Okay. So I believe we've captured the model for this given problem. I guess as usual, asking for any questions, concerns you may have at this point. If not, I'll go ahead and work this one out in Pyomo there, just so I can kind of keep the lecture balanced between Python and Excel. So to do that, what do I want to do? Let's go ahead and close this tab out. And create a new one here. A little bit of boilerplate import there. And the next thing I do want to do before I grab too much of this is just keep it so I don't have to write the code again for this part. There's basically my data import step. All right, so let's start creating a model. So we would say m equals p dot concrete model. Again, concrete model because we know all the data at the time that we create the model. Okay. Remember we could create sets. We would initialize them with a list. That's all good. And then we could get params. So, all right, I'll stop right there. pe.param. Do remember at this point when you start putting in positional arguments into pe.param, same thing with variables, is that it's looking for indexes. And so in this case, our harvest are indexed off the farm. So I would say m.farms. And then I would initialize with a dictionary that I've got like right here, where the keys are the values in the set, and then the values are the values of the parameters. And just make sure that I'm thinking correctly here. We'll pre-print that out. And I have the typical values here, just like we'd want it to. It's very good. So now we have annual cost. Yeah, we'll call it farm cost. So just looking at the annual cost here and needing to map those down into a parameter. Then we have plant demands. Now this one's not based off of the farms, but off of the plants. So I switch the index. And then we've got shipping cost. And here we have to be careful. Be careful because I have to match the ordering of these tuples. Notice I have what? Farm and then plant. So I would need to make it down here farms first, then plants here. Then use the keyword parameter initialize to map in the shipping cost. Okay. All right, so very good at this point. So now what is next? Next we get into decision variables. We need to have x and y, and we can use the same things we were using over here. So m dot x is equal to pe dot bar. Now we are needing to index it, right? So that's what we would do first. And so we could say that is indexed. I'm going to use the same ordering that I used on the right-hand side here. M dot farms, m dot plants. And then we'd say domain is pe dot non-negative reals. This is the same as always. But if I say m dot y, if that's going to be the binary decision variable, it's only indexed off the farm, so I'll start off like that, but then I'll say the domain is pe dot binary. And then I didn't get any errors, so that it is nice and accepted. Okay, so now that we have that, let's look at this objective function here. Let's break this into two different ones just to make it simple or to look at. Maybe we say, hey, obj annual cost is equal to sum. And we can say for f in model.farms, I want to take the sum of what product? I want to take m dot farm cost of f times m dot y sub f. And if I say obj ship cost, it's a sum. In this case, we have two for loops we'd have to write, right? For f in model, I shouldn't say model here, I should say m dot farms, and also for p in m dot plants, I would have m dot ship cost as the parameter of f comma p, and again, ordering is mattering, times m dot x of f comma p. Again, hitting shift enter there at every kind of statement allows me to check for syntax errors, so that's good. And so now I can say something like m dot obj, the expression, or the objective function, is equal to an expression, and all I have to say is obj dot annual cost plus obj dot ship underscore ship cost. And then we usually have to define a sense, right? P dot minimize. And so just to make sure that I'm thinking right, let's see here. Expression, yes. Annual, yes. Right here. This should be PE dot objective, of course, not M dot objective. Now it's PE dot scalar. There we go. And so we end up with a situation like this, where, let's see, that is all of the summation of the annual cost. And this down here would be tied in with the shipping cost. So hopefully that all makes sense. It's not too intimidating. And now we move on to the constraints. We surely have two constraints to write because we're going to use the constraint list. M dot plant, I'll say once, just to make sure I don't reuse plant demand or anything like that, is a p dot constraint list. And notice here we said we were going to walk across the set of plants. So it's a for p in m dot plants, is how that would be rendered in the Python syntax. And I can say the left-hand side, again, looking at this summation, we're having a sum over what? Well, over the set of farms. We would write that. And then we would have here just the m dot x of f comma p. And the right-hand side would just simply be the parameter plant demand sub p. And then we can add the left-hand side must be equal to the right-hand side. And I forgot the M dot. There we go. Just a sandy check here. So we have something that looks about like that. It's an equality here, so the lower and upper bounds are the same. And then we have here, notice that top line is for plant A. You can see all the second subscripts there are A in my little list. And then I have 1, 2, 3, 4, 5, and 6, the different farms going to it. So that all looks good. The next one will be quite similar. Farm harvest. I don't think I've used that as a property name, so let's go with that. It's a PE.constraint list. And again, looking at kind of the right-hand side, I'm looping across all the farms. And on the left-hand side, I have a summation across all the plants. What's in the summation? Well, it's just the decision variable X. Now, the right-hand side, you can see, is a little more complicated, though, right? Because it's the product of my decision variable Y times the parameter that I call harvest in the Python code of that given farm. Now that I've got both sides of the inequality, I can just say m.farm harvest.add. My left-hand side here now is now less than or equal to my right-hand side. No syntax errors there. At this point, we can get a solver. We get a solver out. So solver equals pe.solver factory and reference GLPK. And let's just go ahead and solve it first and see what happens. And we'll t the results. Again, it solves it very, very quickly. And here I'm just looking, I'm solving the LP relaxation. The optimal LP position has been found. And this is what I was talking about before, as far as now it's begun the integer optimization part of it, because I do have those binary decision variables right here. And here's the steps that it's taking. Basically initial stabilization step, but then it found out that it's within 18.1% of optimality. Then it kept working, now 14, now 14, now 9.6, and then it terminated there. And notice the statement here, integer optimal solution found. And I could just say something like m.display. If I could spell display right, and I would come up with the optimal solution. Looks like the optimal solution would require us to purchase farms 1, 2, 4, and 6. Let me check my notes real quick just to confirm we are on track here. 1, 2, 4, and 6, yes. And a resulting value of the objection function total cost. These are in thousands, so it's roughly 2,082,300, so that's good. And then we've got the typical distribution plan embodied in the variable x there. Of course, as always, I would suggest you kind of clean this up for your person that you're going to be presenting this for. We're looking at definitely the raw output of the solver at this point. But one of the things I did want to go back through is kind of illustrate the use of the MIP gap. So in this case, what if I wanted to play around with the MIP gap, and let's say this took forever to solve. Let's say this took an hour to solve, to be more precise. And so we wanted to be able to short it off if it got within 10%. Well, I would do that by saying something like here, I think it's solver options, and specifically it's the MIP gap option that I'm looking to pass it. And if I wanted to stop it at 10%, I would give it the fraction 0 or the decimal 0.1. So let's go ahead and run this, run this. Notice the difference here. Relative MIP gap tolerance reached, search terminated. Before, there was at least one more step after 9.6 that they got the optimal solution. This is PyOmo based, or not PyOmo, but GLPK basically saying, hey, you said all I had to do was get within 10%. well, I'm currently at 9.6%, so I'm going to stop working. I'm bailing out at this point. And so that's the message it's producing, all controlled by this MIP gap that I've introduced right here in that one line of code. Well, in this case, if I look at this result, I don't know if I've run that yet. Let's see, I'm at 23, 24. I think I may be at the same solution here, yeah? Basically, it was basically running one more step to validate that it knew that it was at the optimal solution. So here I could actually bring this up a little bit more, and we can see that it actually does affect. Let's say instead of 10%, we go to 15%, just because one of those steps is 14. Yes. Now it's going to stop at that 18.1, 14.4. The next step would have been 9.6 is the way it's been working. And so now notice as I come down here and look, that's now no longer that 2082.3. It is now 2154.9. So here we basically have been able to tell the solver to stop short, and it has actually affected our resulting optimal solution, and in this case, the cost of the overall plan there. So hopefully that sheds a little bit of light on the MIP gap as far as how it can actually be done. In this case, either way, we were actually solving it very, very quickly. So, I mean, just the idea that if I come back here and comment out this line of code, it's almost instantaneous there. So we typically would not even entertain a MIP gap there, just because we want the true optimal solution, if at all possible. All right, so as I page back to my notes here, any questions, concerns with what I'm showing you? And the Pyomo side of things or the problem as a whole? Okay. I'm not hearing anything, so it's 5:53. I know we've gone a little bit longer here. Shall we need to use Pyomo to resolve the problem? You don't necessarily need to use Pyomo. It's still going to be optional in this case. You could have solved that same problem in MS Excel. I actually have an example of that. If you look at the lecture notes here, this problem right here is the same problem that we just solved using Excel. So there's the same solution that you would have gotten from the Pyomo solution. Have I ever used any other program to solve this type of thing? Is another question. Personally, no. I've basically stuck with using Pyomo for the layer inside of it. I've used Excel, obviously, are the two different ones I've done. There are other ones that exist in the Python space that I do know. Pulp comes to mind, I believe. Model written in Python. I don't know that much about it, but I know this is kind of in that space. What the homepage looks like. Oh, it's just the GitHub homepage. It's a linear and mixed integer linear model written in Python. Oops. And solve them with the latest open source proprietary. So it's going to feel similar to Pyomo here. I don't know if it actually has a solver that comes with it or is baked in, but it sounds like you can write in the pulp modeling language and then call GLPK as well. CBC, CPlex, these are other solvers that are out there. So no, I don't have a whole lot of experience like broadwise in the space. I've more or less stuck with Pyomo. There's a lot of nice features I like with Pyomo, and I've kind of stuck with that at this point. I think there's also other ones out there. Like I'm sure if you looked at some MATLAB or something like that, like a commercial computer algebra system, I'd be very surprised if they didn't have the capability to solve these type of problems in some way, shape, or form. But I guess the underlying theme as I talk through all of that stuff is just the idea to go from a problem statement like this to something that looks like this. I think that is going to be the hard part of most problems, and then it's just a matter of feeding it off to a solver that can solve it. All right, so if you don't mind, I'll kind of go ahead and proceed forward if everybody's doing okay. We have the location problem and then just some commentary type stuff to talk through 7.4. So if we kind of keep going, then I think we may be able to get out even a little bit early this evening. Hopefully we can maybe enjoy some of the sunshine as it's a nice day out today. All right, so another example of a type of problem that is very similar to this farm problem where a facility maybe at a certain location or not is this location problem. One type of problem is like you're trying to gain coverage in a geographical area and you've got a bunch of candidate cities that you're putting things in and you want to gain a sufficient coverage, but you want to do that at the minimum cost, so minimum placement of entities in these given cities. And so that's kind of what this is talking about. So when I talk about these entities, think of them as shipping hubs. In this case, we've got a bunch of candidate cities here, Atlanta down to St. Louis. And then every one of these cities is within a certain radius of all the other cities in the collection. So for instance, Atlanta there on the top is within 300 miles, obviously, of itself, plus Charlotte and Nashville. Now, Boston is only within 300 miles of itself in New York, so on and so forth. Now, the question is, I want to be able to have a shipping hub within 300 miles of every city that's listed in this first column. Given the relationship between a city and its, I'll call it its neighbor cities here on the right-hand side, what is the fewest number of hubs that I need, fewest number of these cities picked, such that I establish that condition that every city has a hub within 300 miles. And so maybe we can just talk through this one. And so, what is the big decision to be made here? Well, if you think through it, the decision really to be made is, do I place a hub at a given city? So if you think of it that way, then the natural decision variable comes out as binary, right? It's, do I put a hub in that decision or do I put a hub in that city or not? So we'd have a listing of decision variables. Let's call them X, maybe X sub C, where the C is the set of cities. Okay, if you think through that, then our decision variables as the decision variable, our objective then is to minimize the total number of these that I have. And so that's what I'm saying here. Let's say I've got a set of cities C. R sub C is a set based off of this index C. So it's basically all the cities inside of that 300-mile radius. So if I'm looking here, if C, this little C is represented by New York, then the elements in this set are Boston, New York, and Richmond. Well, the other idea would be to say, okay, I've got decision variables. They're X sub C. We just talked about that. My objective function is very simple. All I want to do is try to minimize all of the different decision variables that are active. So they'd be ones instead of zeros. So that's what this line's stating. And then subject to, well, here it's nice because all I need to do is write a constraint for every city, forcing one of the neighbor cities. When I say neighbor cities, that's the ones within 300 miles, the ones that are within this R sub C set. Make sure one of those at least is one. And so that's exactly what I'm saying down here. Grab a city from my list of cities, loop through all of the close cities as defined in R sub C, and then sum all the decision variables associated with those close cities such that at least one of those must be one. And that's what we're saying here. Now this is written in set notation, so instead of having to write out, I don't know how many there is, probably a dozen cities here, I can write that as one line. And then I just noticed that, yes, the X sub C's are binary in nature. Really, that's all there really is to this problem. So hopefully that helps as far as this kind of combinatorial problem, as far as which of these cities to use. It becomes very simple when modeled in this type of integer-based programming, or in this case, using binary decision variables. And then I can solve it in whatever form I want after I have this. The PyMO would follow very similar ideas here. What I've done in my Python code is I have a list of cities. Here is a dictionary where that is the city that's the index, and here's all the neighbor cities. And then notice here, my Python code is very, very short. I've got 15 lines total, and I can see 1, 2, 3, 4, 5. I've got about 10 lines of non-blank Python code here where I create a model. That's kind of boilerplate. We create a set of cities. We've done that before. Decision variables, we've done that before. This looks very similar, probably less complex than the one we just did. And then a constraint list like we've done before. But maybe the issue with the constraint list here is this notation here, where I'm looking at the dictionary radius map that I've described here. I'm passing in a key, and then I'm iterating over the items on the right-hand side of that colon. And I'm just saying that's the left-hand side, and they have to be greater than or equal to 1. Those left-hand side integers that I'm summing are those decision variables there. Then I just go ahead and solve it. And it solves out very quickly. And here's just the result. I'm basically looping through the set of decision variables and checking which ones are 1. If they're 1, I'm putting in this list of pick cities. This is going to be what's called list comprehension. And then I'm just printing out that list. So some little bit of fancy Python syntax here, possibly, to basically be able to render out the results being Atlanta, Detroit, Nashville, and New York. If you don't like the Python side of things, that is perfectly fine. You can still do the same thing with Excel. It just becomes a little more difficult. And so what I've done here is wrote the same problem in Excel. I've got this big matrix that looks like it's going to describe the city and its nearest cities. Here are the decision variables. I'm just minimizing those decision variables there. And what have I done here? I'm basically one at a time trying to keep track here of which ones to do, but as you can see, I'm selectively placing the sum to be the near decision variables on the left-hand side of each of these constraints. So I'm doing it fairly manually. This is where I don't like doing these things, the types of things in Excel, because it's somewhat meticulous to do it this way, very error prone, just to make them clerical errors for most of anything, not logical errors that are a little bit more serious. And the fact that I'm saying are greater than or equal to ensures that at least 1 is there, but notice at times there are more than 1, right? Like Nashville is going to end up with 3 different hubs within that 300-mile there. But we're all taking a short, not taking a look at it locally with respect to Nashville, but remember we're trying to optimize this at a global scale with respect to the entire region here, if you will. So I know I may have went through that one relatively quickly, but I think that we've kind of pieced together a lot of these building blocks throughout the evening. But is there any questions or concerns over what I just described in this location problem? And as I pause here, I'm going to go ahead and save this one before I forget. Okay, not hearing anything. Let's get into the last bit here. We've started seeing a little bit, especially with this, when I was saying things, at least one shipping hub had to be within 300 miles. And so let's kind of expand on that a little bit more in kind of a little more generic sense. These binary decision variables are really powerful. Hopefully you're starting to see that. And 7.4 basically just talks about some recipes, if you will, of how these can be applied to more logical statements. And so in each one of these, we're going to have mutually exclusive decision variables that are binary. Those are just the x1, 2, and 3 in this case. And so, for instance, if you write something like this right here, x plus 1 plus 2 plus 3 equals 1, that forces one and only one of those decision variables to be active, to be 1, which of course makes sense, common sense when you look at that statement, but it's worth saying. And then over here, a slight twist of that directly below it, this statement here is saying at most one of those decision variables is active in 1. which again should make sense because you'd have 1 that's 1, and all of them be 0, and that would be satisfying this condition. Or you could also have them all 0, and it would still satisfy this condition. And so first, once you grasp that one, you can extrapolate that a little bit more to what we're saying here, k out of n alternatives. So again, think of the x decision variables as being binary and mutually exclusive. Now, if I had to have exactly 2 of them to be on or active, then I would write something like this. But if I want to say at most 2, I could write something like this. Again, whether I'm forcing an equality or letting it be a little more looser toward the lower end with that inequality. And so that's kind of another step toward this evolution. And then we have this last bit here, which is conditional and co-requisite. These are a little bit more complex here. And so what do we have here? We have a decision variable x and a decision variable y. And so instead of just being abstract, mutually exclusive, let's let them actually model real things. So let's say x is a binary decision variable to describe I'm purchasing new equipment. 1 if I did purchase it, 0 if not. Y being another decision variable with the expansion of a production area. 1 if I expand, 0 if not. You can kind of see where this is going. If I buy new equipment, I may be required to expand the production area because I physically don't have enough room to put it. Those type of questions are coming to mind. So let's look at this conditional constraint. Well, constraint would be saying things like, if the equipment is purchased, then the production must be expanded, or in short here, if X, then Y. How would I go about modeling this? Well, to determine the inequality, the equality that you need to write, you would first want to create what would be called a nice little truth table here, a feasibility table. And so what I've done is I've got 2 different decision variables modeled here in the first 2 columns. And I've basically, in those 2 columns, developed all the possible combinations of 0 and 1 that I could have here. Well, there's 2 different decision variables. Each of them have 2 different possible states, 0 and 1. So there's going to be 4 different total combinations here. And then I look at the relationships that it must be applied here. Well, this is if x is equal to y for the top and the bottom. And then some of the ones below I could say are greater than or equal or less than or equal to. Well, does this make sense in terms of, well, if I have the x is 0 and the y is 0, that means that I did not purchase the equipment and the production area was not expanded. Okay, that works, right? If x, then y. Yes. Down here, I did purchase the equipment and then I expanded the production. So that also works. Here, this one, I purchased equipment, but I do not expand production. That breaks, right? Because the condition is if the equipment is purchased, then I must expand production. So that is false. Here, my x is 0 and my y is 1. That means I didn't buy the equipment, but I did go ahead and expand the production. Well, that could also be true, right? Because I'm basically saying if the equipment is purchased, then do this. Well, if it's not purchased, this no longer applies, so that is fine. And so you start looking at these and say, okay, where are all the cases where this is true? I've got 2 equalities and a less than or equal to. So the kind of more generic one of those 2 is the less than or equal to. So I can state that this logical constraint can be applied with a simple constraint that looks like this in our LP model. Again, rendering it back down to something that I can pass to a solver and that I can solve. Well, there's a slightly different way of saying this as well. And that's what we have here is a co-requisite constraint that says if the equipment is purchased, then the production area must be expanded. Also, if the production area expanded, then the equipment must be purchased. So if X then Y, and if Y then X. I do the same exact logic here, except I end up with a scenario here where basically both of them have to be equal to each other. In this case, I don't purchase the equipment, so I don't expand. So that's true. In this bottom case, I do purchase the equipment, so I do expand. That's also true. Anytime they're mixed, where I make a purchase and don't expand, or I don't make a purchase, but I do expand, those are all false. So I see that this logical condition here that is described in this unordered list item there can be easily expressed as a constraint of x equals to y there. And again, this type of idea should be able to be extended more and more if you had more decision variables that then had to interact with each other. We won't go into a lot of those cases for the homework problems or anything like that, but just give you a kind of a path to follow moving forward. And believe it or not, that completes our lecture this evening. This is one of the areas, again, the longer I teach this class, the more I think we need to embrace this area and kind of dive deeper into this area of NIP problems. But unfortunately, at this point in me teaching this class, I haven't had the time to more flesh this more out there. But again, even with what we've described tonight, hopefully you can kind of see the power of it and the new types of problems that you can solve with these integer and binary constraints on, well, integer and binary conditions, I'll say, on our decision variables. So at this point, I guess I'll turn to the audience as far as any questions, concerns this evening as a whole. Not hearing anything right off the bat, so I guess I'll go ahead and turn over to the kind of more administrative task here. Here is the homework set this week. I don't believe there's that many actual questions there, so that's why you have the 3 total attempts. That's new. Usually it's just 2. It is self-graded, takes the highest. The other thing is that my understanding is that spring break is upon us. It's Thursday evening. There's one more business day before spring break next week. So I hope you guys enjoy spring break. Take some time to relax a little bit. Maybe let your brain rest, so to speak, there. So with that in mind, the due date here is not the 20th notice, but is the 27th. So the next time we'll actually have in class there. And so by all means, if you have free time and you want to jump into this, I will be checking email and all those things over in spring break next week. I don't really have any major plans there. So feel free to get started early, but also know that it's not a firm requirement there because you do have basically 2 weeks from this evening to complete the homework set. And so I guess with that being said, that's all I have for the evening. I'll stick on if there's any questions, but if you're satisfied at this point, feel free to hop off the call and have a good spring break. Show the question numbers is one quest. So looks like problem 8, problem 12, problem 14, and 23, and 25. I guess I'm not hearing any other questions. I guess Jared, since you are still on the line, I think you did reached out about your Excel installation giving you issues. I don't really have any a whole lot of expertise there, but if you want, we can hop on a different Zoom meeting to take a look at that. If you want to do that, or it's kind of up to you.
Can you hear me?
I can hear you now.
Can you? Oh, okay. I didn't know if this worked. I'm actually at home with a sick kid, so I'm using a different machine, so I
Okay.
can't even really look at why my Excel's not working. But
Okay.
it's a much newer version than what you've got there, and the solver functions the same, but it looks a little different. But
Yeah.
I don't know if I can delete it or uninstall it and try and reinstall an older version. I don't even know if they let you do that, but.
Yeah. It's one of those things I haven't had to do any of that kind of stuff for quite a while. So Um,
Yeah.
the only thing that I was thinking of, not to spend too much time talking about this on the lecture video, was is that a personal machine or is that a machine you use for work?
Yeah, I mean, I own the business, so yeah, it's a work computer, but
But you didn't like push
uh,
out like a group policy or anything like that to it that you're aware of?
no, nothing like that.
Yeah,
I think
I'm just
it
trying to
probably
think of.
just updated on.
Okay, if it's a Windows update, on some Windows updates you can actually revert the update. That would be one potential thing to try.
Yeah.
You can actually go into the Windows update and try to revert it to whatever happened recently. Depending on the update, I think that's an option or not. Sometimes there's security updates that obviously you don't want to do that to. That's the only thing
Hmm.
that really came to mind there as far as with your situation. Just trying to get back to again what happened, you know. I
Yeah.
guess the other
Yeah.
side of things, the good news with respect to the timing of this throughout the semester, um, the Excel solver, I think, is what you're saying does not work, but the other things do work, like your regular spreadsheet functionality. We have this week that we
Yeah, it
definitely
does.
next week is nonlinear, so we would need the solver. After that, it kind of takes a little bit of a break. When we talk about queuing theory and inventory, think some of forecasting even as well. Maybe allow you to use that same machine with Excel without having to use the actual solver part of it. And so we do have some topics coming up that don't have a strict prerequisite on the solver. So I guess what I'm trying to say.
Yeah. Okay.
So
Well, I'm going to
just
keep working towards getting it fixed, but
yeah, I understand that'd be
I'm
a
going to
great.
try to do it in R as well.
Yeah. All
Yeah.
right. So I guess best of luck with that. If you want to ask questions, you can. I just don't know how much expertise I can really offer there.
Yeah, no, I don't blame you there. I just it took me for a back because it worked perfect right up until, just one day I tried to redo it and it wouldn't work. I
Yeah.
even opened some of my old homework where it had worked and tried to run it again and it wouldn't work there. It just freezes up, it doesn't.
Yeah. And that may be one thing. I've never tried them, but the Gorilla Geeks on campus, it may be worth a shot
Yeah.
talking to them. But again, I don't know how much they would know about the intricacies of the Excel solver.
Yeah, that's true. Yep. Yeah, I've got one really good IT guy to reach out to, and I'll probably do that in the next couple of days and just to see what he has to say.
Sure.
So,
All right. I guess let me
all
know.
right. Well, thank you.
Yep.
Yeah, I'll let you know if I come up with a solution.
Yeah. It'd be good to know just to have in my back pocket for future students that may come across that issue.
Yeah. All right. We'll see you in a couple of weeks.
Yep. See ya. Have a good one.